So next up, we have Zeromorph, Zero Knowledge Multilinear Commitment Scheme by Tohru Kohrita at Aztec.
Thank you for the introduction and this nice opportunity to talk about Zeromorph. This is a joint work with Patrick Tova, who is he's my colleague at the Aztec lab. And I'd like to also give thanks to Ariel, who is here today, because he helped me a lot to learn the basics of the commitment schemes when I was working on this project. Okay, so the plan of the talk is the following. Now, we first talk about what the Zeromorph is, and this is a polynomial commitment scheme. And then, so we talk about the commitment algorithm, evaluation protocol, and finally touch upon the cost evaluation of a particular instantiation with KZG polynomial commitment scheme. So what is Zeromorph? It is a recipe to obtain a multilinear PCS from additive univariate PCS with degree check protocol. By degree check protocol, I mean the protocol that allows the verifier to check the upper bound of the degree of the committed polynomial. And we require this degree check protocol to be knowledge sound. So first, I will talk about a little bit of the motivation behind this work. And that is we are interested in this sum check-based proof of circuit satisfiability. We expect that the sum check-based proof is more efficient than the traditional univariate Plonk proof system. But to use the sum check-based proof, sum check protocol, we need to have a multivariate commitment scheme. And that was the background of this project. And so the Zeromorph is based on the same multivariate polynomial equality check as the multilinear KZG, but we do this with univariate commitments. If you follow the recipe, and if the underlying commitment scheme is hiding, and the underlying evaluation protocol is ZK, and the degree check protocol is ZK, then the resulting Zeromorph evaluation is also zero knowledge. So so jump into the commitment algorithm. So the idea is to convert multilinear polynomial into a univariate polynomial and commit to it using a univariate commitment algorithm. So here, what we have to do is here. The source of this map denotes the vector space of multilinear polynomials in n variables, and the target is the univariate polynomial of degree at most 2 to the n. Our goal is to make a nice map between them. The two vector spaces are abstractly isomorphic, of course, because they have the same dimension, 2 to the n. So the question is, what is the most suitable isomorphism for our purpose? And the map we use is the following. Like n equals 1 case, the bivariate case, this is the simplest one. We map the bivariate multilinear function f to the univariate polynomial whose coefficients are evaluation of f over Boolean points. But the question is how to, and the way we place this evaluation of a Boolean points is the following. The red lettered ones, these are what is this? Boolean points, and we interpret it as binary representation of integers. For example, 0, 0 represents integer 0, so we place it as a coefficient of the degree 0 term, that is the constant term, and 1, 0 represents integer 1, so we place it as a coefficient of the degree 1 term. So the left is the least significant bit in this convention. And 0, 1 represents integer 2, so we place the evaluation over 0, 1 as a coefficient of degree 2 term, and so on. And this obviously makes sense for any n. So for the general case, we have this isomorphism, and we use this one. And we call this curly U to remind ourselves this is a univariatizing process. So So general case, the multivariate polynomial f is mapped to the univariate polynomial u of f. The coefficients are the evaluation over Boolean points f of b0 to bn minus 1. And we place it at a coefficient of the corresponding degree. To commit to f, the multilinear f, a zeromorph prover commits to u of f using a univariate commitment scheme. And the reason we choose this map is the following. So we are interested in this proof of circuit satisfiability, and the prover of this kind, the prover usually starts with witness values, and witness value, and then he takes the multilinear extension of it and then commit to it. But the u of f is free for such a prover because he started with the coefficient of the witness values itself. So now the evaluation protocol. We have the univariate commitment to u of f, and we have to open f itself, not the u of f. So this is the non-trivial part. So to explain the evaluation protocol, let's fix the notation. F is the commitment polynomial, n variable multilinear polynomial, and z0 to zn minus 1 is a point in fn. This is the evaluation point. And the claim to prove is that f evaluates the v, the value v, at this evaluation point. And we know that from the, this is well known, that this statement is equivalent to the existence of qi, the polynomials, such that the equation 2 holds. This is the usual multilinear KZG evaluation equation. So over here, I wrote in red xi minus 1. This is a condition. This is a tacit claim I'm making here, and we force the prover to follow. We force the prover to find qi that is a polynomial only in the first I variables. And we are going to use this in Zeromorph later. So this is the point to force the prover to do it. OK, so back to the usual multilinear KZG. What the verifier does to verify the equality 2 is the verifier receives the commitment to qi from the prover, and then he uses elliptic curve pairing. But for Zeromorph, we are not going to do that. But what we are going to do is to apply the the isomorphism in the previous slide, to the both sides of 2, make it into a univariate polynomial, and the verifier check the equality at the challenge point. So this is what we are going to do. So the verifier needs to check that there is qi satisfying this condition on the variable that satisfies such that the equation 3 holds. So suppose that the prover provided the commitment to u of qi, then the verifier can use the univariate evaluation protocol to evaluate u of qi and u of f at the random point, and verifier can compute u of v at the random point by itself because it has a nice explicit formula. The question is, can verifier evaluate u of xiqi at the random point? And the way we do is this, a nice fact. U of xiqi is actually a product of u of qi and this fraction. So and for this fact, we use that qi is a polynomial only in the first I variables. So throwing this one into the previous equation, the verifier needs to check this equation 4. F evaluates to v if and only if there is qi, satisfying the condition on the variable such that equation 4 holds. Now, if you have a commitment to u of qi, then you can evaluate both sides at a random point. The problem now is to make sure that qi satisfies this variable condition. And the way we do this is this. Qi is honest if and only if there is univariate polynomial Ri of degree less than 2 to the I, such that u of qi is a product of Ri and Vi. And Vi is a polynomial written here. It's in a fraction form, but this is divisible, so it's a polynomial. So throwing this fact into the previous equation or the principle, we obtain this. F evaluates to V if and only if there is Ri of this bounded degree such that this last equation holds. Now, if you have a commitment, so that it goes like this. The prover computes and commits to Ri, and verifier and prover engage in the univariate evaluation protocol and then evaluate both sides at a random point, and then verifier and prover engage in the degree check protocol to make sure that Ri has a bounded degree. And by the way, that last equation can be written in a slightly slimmer way. I just used that Vi divided by this chunk is Vi plus 1. It's just an algebra here. So this is the equation to check. So evaluation protocol. P computes Ri and commits to univariate commitment. Commits to Ri using a univariate commitment algorithm. P and V engage in degree check protocol to make sure that Ri has the correct degree, and also degree of U of F is less than 2 to the n. I haven't talked about this yet, but I'm going to mention this last check later. V chooses a random nonce at challenge point A. P and V engage in the univariate evaluation protocol to verify that capital F takes the value 0 at x equals A. So if f of x takes the value 0 at x equals A, if you throw the plug x equals A on the right-hand side, you see that this is just the right-hand side minus left-hand side of the equation in the previous slide. So this is about, yeah. Okay. And then the reason we do f, the final one, in this way, because it's much more efficient than opening U of F and Ri of X individually. And also, if you do it this way in one go, you do not need to review the evaluation of U of F and Ri of X at the challenge point. And this is handy because we have less transcript, so it's easier to make it into zero knowledge. Okay, and maybe I should also say that note that the verifier can simulate the commitment to F using the commitment to U of F and then Ri of X. Okay, so if univariate commitment scheme is hiding and ZK and degree check is also ZK, then Zeromorph is ZK. This is a fact. Okay, about the degree check on the U of F. So we wanted to prove this evaluation, the knowledge soundness of this evaluation protocol in the standard model. And to do that, we need to extract the small f, but then we do not perform the actual evaluation, univariate evaluation on U of F, so we couldn't do that. There's no way to do it, and therefore we invoke to the knowledge soundness of degree check protocol, which we assume. Okay, so finally the cost. Because this evaluation, by the way, doesn't look so efficient, but if we instantiate it, if we use the KZG protocol univariate commitment scheme as an underlying commitment scheme, we can merge for step 2 and 4 together and then do some optimization, and we can achieve the following. The capital N is, okay, let capital N be 2 to the n, the number of coefficients of the commitment polynomial. The prover cost is G1, so G1 means that the first pairing, okay, the underlying univariate commitment scheme is KZG, so there is a pairing. We use the elliptical pairing, and then G1 denotes the first pairing group. So prover cost, G1 MSM of size n plus 1 for commitment, G1 MSM of total size 2.5 n plus 1 for evaluation. Total size means it's not just one polynomial, it's actually several polynomials, and the total number of coefficients, the size of the MSM is 2.5. And verifier cost is the G1 MSM of, again, total size 2 log n plus 2, and 2 G2 operations, 3 pairings. Proof size is logarithmic, and we use the log n plus 2 random nonces, This is kind of optimal because in this instantiation, log n plus 2 is exactly the number of independent transcript that prover produces. And finally, the evaluation protocol is constant round and 5 rounds. Yeah, that's it. Thank you.
Awesome. Thank you, Tohru. Do we have any questions for Tohru?
How do you compare this with the tensor check that we did in Gemini? Because we had only 2 pairings for just like a couple pairings for verifications without all these MSMs.
Yeah, so for Gemini, I counted the performance and the open protocol after some optimizations and using the Splunk protocol. First, Gemini, you need to open the evaluation at multiple points.
Yeah, that's the standard batching technique. Yeah.
And so the evaluation protocol cost at least 3N, and Zeromorph costs 2.5N. So
3N MSMs?
Yes, 3N MSMs. But this is like a log n number of 3N divided by log n MSMs. I'm sorry.
You just need to compute one quotient.
No.
In Gemini.
No, you have to commit to the folded. Folded polynomials.
Okay.
There are logarithmic number of
so
them.
So that's the 2N where it comes from. Okay, I see. Thank you.
Yeah.
Okay, nice. Yeah, we're done.
Any other questions?
Thank you, Tohru.